Mhm. Mhm. Okay, good morning, everyone. Okay, so I saw your questions, so I will start by going over your questions, okay? So we start with number 21. So we have the following graph, and they gave it to us, 1 over the square root.
I got a dream. I got some dream. Oh, somebody.
Please mute yourself. Thank you. Okay, so we have x equal 1 over the square root of 1 plus y squared. So they are definitely giving us x as a function of y. X equal to 0, y equal minus 1, y equal to 1. That's the region. And they definitely drew the region for us, so that's the region. Now x equal to 0 is the y-axis, y equal to 1, so this is y equal to 1 right here, y equal to minus 1, and the graph which looked like this. So we can erase this piece. Okay. So this is the region. And we are rotating it. Yesterday I did rotation about the x-axis. And today I ask a question about the y because the thinking is exactly the same. Okay, so basically we're going to rotate this around the y-axis. So we get like a barrel type shape. And the question is, what's the volume of this object? The approach will be the same. Okay, we are going to cover this with little cylinder, with very thin cylinder. But instead, when we rotate it about the x-axis, the cylinders were vertical. So we cover this whole region with vertical cylinder. In this case, we're going to cover them with horizontal cylinder. So you can imagine this barrel and we fill it up with little cylinder. So how are we going to do to generate the cylinder? So instead of taking, like yesterday, instead of taking those vertical rectangle, we're gonna take horizontal one. Okay. And whenever I rotate this piece, I'm gonna get my little cylinder. And I add those cylinders. So this is, we're gonna talk about typical disk. In this case, from here to here, so I'm gonna call this Y. This is the delta Y. And so when I'm rotating that cylinder here, I'm getting that piece right there. This is the little cylinder I'm getting through my rotation. So the radius is going to be from the y-axis all the way to the head of the curve. That's going to be the radius. Okay. So which is going to be equal to what? If I have, this is the y from here to here, it's the x, is the horizontal distance from the y-axis till I hit the curve. It means the x that correspond to this y. It means 1 over the square root of 1 plus y squared. So if this is, let us say I give the y the value a half. If from here to here a half, from here to here, it's 1 over the square root of 1 plus a half square. That's really the idea. So typical disk. The radius of it is 1 over the square root of 1 plus y squared. So everything in terms of y in this case. And the little height of it, or the thickness of the disk, is the little delta y. The volume, because I'm adding volume now, the volume of the disk is basically the area of the base of the disk. It means pi times the radius square times the height of it, which is my delta y. So finally, this is equal to, so that's one disk, 1 over the square root of 1 plus y square times the delta y. So that's one disk. Now, the volume of the solid at this stage, I think that what I'm actually doing is I'm going to subdivide this into pieces at this stage and cover it with all those little cylinders. So you're gonna have, you can imagine this whole barrel covered with one little cylinder on the top of another, on the top of another. So that's what we are doing. All those cylinders are horizontal. So it's almost equal to the sum of the volume of those cylinders. At this case, I put yi because I'm thinking that I am subdividing them into pieces. The last piece is the integral. This is a typical Riemann sum. When n becomes very large, so the volume is going to be the integral of, pi times this quantity squared. Y is my variable, dy. I go back to the graph, which interval I need to divide to cover this whole region from -1 to 1. So this is the -1 here, and this is the 1 up here. And the rest is we have to evaluate this 1 square. Now this will be equal, the integral from -1 to 1. Pi is a constant, I can take it out. And the squaring this quantity, so I'm left with this piece right there. Okay, so finally I am basically done. Antiderivative of 1 over 1, 1 plus y squared. I think we've done this several times. That's the arctangent of y evaluated between -1 and 1. So now pi is a constant. The value at the upper minus the value at the lower. So arc tangent 1 minus arc tangent -1. So finally, I get, this is equal to pi. Arc tangent 1, the angle whose tangent is 1 is pi over 4. The angle whose tangent is -1 is the minus pi over 4. So finally, I will get pi squared. We have the pi from here, and we have the pi from the arctangent, so it's giving pi squared over 2. Questions about this homework? So rotating about the y-axis is actually the same thing, but instead of taking those horizontal, instead of taking the vertical slices, we're taking horizontal slices. So we're covering with horizontal cylinder instead of vertical cylinder. Questions about this problem? Okay, so we look at number 21 quickly, and then we look at 30 and we move on. So number 21 or 22, I don't know, 22. Okay, so it's the same thing, but they are just changing the region. So the concept is not changing. So again, we're rotating around the y-axis, and this is the region. They have a graph like this, and they have a 2 in here. Right here, they have 1. And this is y equal ln of x. So that's the graph here. And the region in question is this region here. Okay, so they are rotating that region around the y-axis. So basically, we're rotating that. So we're getting kind of a nice ball in here, and that's the base of the ball. So that's what we're getting when we rotate. And the question is find the volume of this object, a nice ball. The principle, as I said, is verbatim the same, but instead of taking those type of slices, so what we are going to do is cover this region with horizontal cylinders. So one cylinder on the top of each other and add the volume of this little cylinder. So we start focusing on only one of them and then we add them. So this is 0. So this is my y. And this is how we get my cylinder. So this is delta y. This is my little one. And we're going to rotate this. Now you don't always have to draw the picture as long as you understand. So we're going to rotate that. So that's the idea here. And now I want to find the radius of every piece. So typical cylinder, typical disc. The radius, the height, which is in this case, I have to start asking you questions, and finally the volume. Okay, now I stop and I go back to you. What is the radius of this disk? What is the radius of the disk?
ln
Of
x.
X.
ln of x. True or false?
You
True.
have to make it y.
ln of x measures what? What the y equal n of x? I will go down here because this has to be crystal clear in your mind. This is the graph of ln of x, right? When you tell me ln of x, what does ln of x represent? If this is x, ln of x represents the distance from the x-axis till you hit the curve. This is ln of x. Are you with me?
Yeah, I got you. So it's
Are you,
actually
all of you, are you with me? It's crucial. It's
Yes.
crucial you understand the concepts here. This is ln of x, is the vertical distance from the x-axis till you hit the curve. Is this what you want in this problem? Is this what you want?
No,
What do you want?
you want the y-axis.
Right, we want this horizontal distance from the y-axis till you hit the curve. When you are dividing the interval on the y-axis into pieces, for you, you know y. Y is what you know. In this situation, you know x. It's you know the y. What you want to find is the horizontal distance from the y-axis. It means from here all the way to here. That's what you want. That's what the radius. So what are we supposed to do to be able to find the radius?
Solve for x.
We have to solve for x exactly. Absolutely crucial. You know why. In my mind, I know why. I want this one. I want this vertical distance. So I need to solve for x in terms of y. So let us do that also slowly in this problem. How can I solve? So I will add here. We need to solve. I will put it up for x in terms of y. Crucial. Very, very crucial. Very good. So let us do that. So how do we solve? X is ln, sorry, my apology. I'm going to do that here. I need room. So we have y is ln of x. So I need to solve for x. How do I solve for x? Exactly. X is e to the y. So you need to solve for x. You can raise both of them. If you remember, you're fine. If let us say you forgot, e to the y is e to the ln of x. Remember, you want to isolate your x. So this is going to give me that x equal e to the y. Absolutely correct for those who put the answers. All right, so to be able to do this problem, x is e to the y. So my radius from here to here, so if this is y, this is e to the y, and that's exactly what I want. So I have the y in this problem. It's the x that I wanted. So my radius is e to the y. Is that make sense? The height is my little delta y. That's the height. The volume is pi times the radius square, which is the area basically of the circle. You times it with delta y. So that's the volume of one little cylinder. When you do that, you're basically done with the problem in a way. So now what is the volume of the whole region? So it's almost equal. And at this stage, I am adding the little volume. So pi e to the yi squared delta y. Now I'm adding them in my mind. It means I'm filling this with those little cylinder and I am adding. So when n becomes very large, the definition of definite integral tell me that's the integral. E to the y squared dy. Interval of integration, you always go back to your graph and you ask yourself, to cover the region, I should divide which interval, the interval from where to where into pieces. We have to divide the interval from here, that's a 0, all the way to here, that's a 2. So to cover this region with those cylinder, I have to divide the interval from 0 to 2. So this is the integral from 0 to 2 of that. All right, so that's the setup. Now let us evaluate. So that's the integral from 0 to 2. Pi is a constant, I take it out. E to the y squared, it means you multiply the power, it means e to the 2y dy. Okay, and now I need to evaluate this integral. How do I evaluate this integral quickly? How do I evaluate this integral?
U sub
We have to
Substitution.
equals 2y.
Absolutely. U is 2 to dy. I have an inside function. I have to do that. The du is 2 dy. And now we can change the limit now or at the end, but the limit are easy. I'm going to change the limit. If y is 0, u is 0. If y is 2, u is 4. Once I change the limit, I am practically done. So now this will become the integral. Pi times. The 0 went to the 0. The 2 went to 4. E to the 2y is e to the u. The dy is half the du. So finally, I will get pi over 2 e to the u evaluated between 0 and 4. I don't go back to y anymore now. Pi over 2 e to the 4 minus e to the 0. E to the 0 is 1. End of the problem. So one important thing about those problems is always to think, what is my variable? Is it x my variable? It means, am I dividing the interval on the x-axis into pieces? That's when x is the variable. Y the variable? Am I dividing the interval on the y-axis? If I'm dividing the interval on the y-axis to cover the region, it means y is my variable. It means we have to express everything in terms of y. It means you know y and you want everything else to be expressed in terms of it. Okay, so we finalize with number 30. And then we'll introduce what you'll be talking about on Monday. So number 30. Okay. Y equal the square root of 25 minus x squared. Y equals 0 about the x-axis. So this is the region that I want us to rotate about the x-axis. Right? So first a word about this piece. because we need to graph it, but I think you guys are at a stage where we should be able to start recognizing the graph of this function. Anybody have an idea what's the graph of this function?
Is it a circle?
Exactly, that's half a circle. So I open my parentheses and I will remind you. Let us recall that if you have the equation of a circle, centered at the origin with radius r is. So if you have a circle centered at the origin and the radius is r, and you take any point here on the circle, so this is your x and this is the y. Pythagorean theorem tells you that x squared plus the y squared equal the radius squared. So the equation is x squared plus y squared equal r squared. Close my parentheses. Okay, so that's a happy circle. So that's really the equation of the circle. So now if I have, so this gives me, so from here, if I solve for x in terms of y, this will give me x is plus or minus the square root of r squared minus y squared. So in terms of a circle, this piece here, I want y, my apology. It doesn't matter actually, but I want the y. It means the top part of the circle is square root of r squared minus x squared. So that's the top part of the circle. And the bottom part of the circle, this is the minus the square. So since I talked about it, now I expect you to be able to recognize this when you see it. So now I have, go back to number 30. Okay. So now we have y equal square root of 25 minus x squared and y equal to 0. So this would become half a circle, the upper half, where the radius is equal to 5. So this is nothing more than the equation of a half circle with radius 5. So here r squared is 25. It means r is equal to 5. So this is 5 and this is minus 5. And we're going to rotate this around the x-axis. And everybody yesterday, when I asked, what do you get? You told me, of course, we're going to get this sphere. And the question is, what's the volume of this sphere? Okay. All right. So we'll do verbatim what we've been doing. So we're rotating about the x-axis. So I'm going to take my typical, so basically we're finding the volume of a sphere of radius 5. So this is my typical rectangle. This is my x here. I rotate it. I'm getting my little disk. Okay, and the question is, as I did before, typical disk, let us see all its dimension. Basically adding the volume of those little cylinders. The radius here is, this time to cover the whole region, I have to divide, I'm dividing the interval from -5 to 5 on the x-axis. So x really is my variable, everything in terms of x. So this is my x, and so this is my radius. If I know x, the radius as a function of x is 25 minus x squared. So in my mind, what about the y equal to 0? Y equal to 0 is the x-axis. Y equals 0 is the x-axis. So this is y equal to 0. Okay, so I'm taking the upper half. So the radius is the square root of 25 minus x squared. The little height or the thickness of the disk is the little delta x that we want it to be very, very tiny. So the volume is area of the base. It means pi times the radius squared times the little delta x, because the delta x make it a volume, and I really want to add volumes. So this is the square root of 25 minus x squared. We know that that's 25 minus x squared. I'm just keeping it like this just to remind us that we're squaring the radius. So finally, the volume is, I will skip the Riemann sum, is integral of pi times the radius squared times dx. So I read it in my mind. I'm taking the area of the circle, the base of the cylinder, multiply it by the little delta x. I'm getting a volume. So we should see volume inside. And this is the square root of 25 minus x squared. And this is the integral from -5 to 5 because I need to cover the whole thing. The rest is a simple integration. So I will have pi times integral from -5 to 5. Now I'm squaring the square root, so this is leave me with 25 minus x squared dx. Okay, and now we just evaluate. Would the formula be, we should get that. Yeah, we should get that. If you don't get that, it means what I'm doing is wrong. Are you with me? We should get exactly what you said. It's 4/3 pi r cubed. So now let us see if we get it. So this is pi times. No, we're not using the formula of a sphere. We're actually deriving it. Are you with me, Aaron? We're deriving it. We're not using it. We're actually finding that formula. So here I will have 25x minus 1/3 x cubed evaluated between -5 and 5. So finally, I will get pi times the upper minus the lower. Okay. Now, the upper, I will have 25 times 5, which is going to give me 25 to the power 3, minus 1/3, 25 to the power 3. So this is going to give me 2/3, 25 to the power 3. Because I have 25 to the power 3. It's not, sorry. I have 5 to the power 3. Because here I have 25 times 5, that's 5 to the 3, minus 1/3, 5 to the 3, which will give me 2/3, 5 to the 3. Right here, I will have minus 5 to the 3, and a minus is going to give me minus 2/3, 5 to the power 3. If you don't believe me, just do the math again. So it's equal to pi times 2/3 minus minus 2/3 will give me 4/3 times 5 to the power 3. And that's, as Aaron said, that's exactly the volume of the sphere that you guys find at the end of the book. So the problem here is derive it, not use it, just derive it and then check, are you deriving it correctly? That was my radius. And so the answer is 4/3 pi, the radius to the power 3, which is exactly the formula for a sphere. Any other questions? Okay. So now, but
Professor Elias, I'm so sorry. Where did you get the 2/3 from? I missed that. I apologize.
don't worry about it. I plugged in 5 here, right?
Mm-hmm.
Okay, so 25 times 5. Okay, I thought of it as 5 to the 3,
That makes sense, yeah.
right? And
Mhm.
then I said I have 5 to the power 3 minus 1/3, 5 to the 3.
Right. Yep. That makes sense.
Yeah. And then 5/3 minus 1/3 would leave me with how much?
2/3. Okay, I see. Okay, that's a clever way of thinking it. Okay, I got you.
Okay, just to make life a bit easier. Sometimes we can, sometimes we can't.
No, for sure. All right, thank you.
Sure. Any other questions? Very good. So before you guys, of course, start take the quiz, which will open in 2 minutes, and what we're gonna do next. So what we did now is the following. You don't have to write. We're gonna work on this next time. We had a region. That's what we did. We rotated it about the x-axis. Okay, and we got that piece. And to find the volume, we said, we're gonna rotate it piece by piece. So we took this little piece. Basically, we rotate this little piece. and we got the disk, and we added the volume of those disks. All right, next time what we are going to do is a little bit different and a little bit the same, basically. So it's still volume of revolution, and we're gonna take a graph, something like that, but instead of taking the region below, all the region below, we're gonna take a region between the graph, this piece right there. And this is the one we're going to rotate. So we rotate here, we rotate there, and then we rotate like this. So we're gonna get this region right there. So we're gonna get a solid with a big hole inside. All right? And the question is, what's the volume of the solid? All right, so the change we're going to do is actually, instead of taking the whole region under the graph, we're taking a region between two graphs and rotating it. And the question is, what is the volume of this new region? So we're going to have a huge solid, but we're going to have a big hole in it. I mean, the hole can have any possible shape you can imagine. The logic is going to be the same, but there's going to be a little bit difference in the geometry. So the logic is the same. It means that I'm gonna take this one and that one, and I'm gonna work with the same idea. So I'm gonna take those little rectangle, but now is the difference. When I'm gonna take this rectangle, which is not touching the axis of rotation, and rotate it, what do you think I'm gonna get? Am I gonna get a disk?
No.
No, because there is a big hole in here. We're not touching the axis of rotation. So what do you think we're gonna get when we rotate this?
A disc with a hole in it?
Exactly, we're gonna get a disk with a hole in it. And that's what we are going to do. We're gonna get a disk with a hole in it. We're gonna find the volume of this disk, add volumes, and finalize the problem. Okay, so we're gonna do very much the same thing, but there is a little bit here difference in this case because the rectangle is touching the axis of rotation. I am getting this disk. Now, when it doesn't when it doesn't touch the axis of rotation, there is a hole in here. So when I'm going to rotate, this is going to stay empty. So this is going to stay empty. So I'm going to get something like that. And then we're going to add all those little pieces. And those pieces, this was a hole, as you guys rightfully said, we are going to call them washers, which is nothing more than a disk, but there is a hole in between. Okay? All right. I think the quiz is open right now. Get going. Good luck. You know how it works. You guys go to activities, assignment, and do exactly like last time. I was able to read every one of you. Okay, so I gave you this time. I opened it till 12:30, but it will close at 12:30 exactly. So I will not give you extra time after that. Okay, good luck. And I'm with you like last time. If you have any questions, you let me know. Get going.